Welcome to our brief look into the world of differential geometry. Differential geometry combines calculus and geometry, unlocking the secrets of curves, surfaces, and their higher dimensional relatives. At the heart of differential geometry lies the concept of the manifold, a mathematical space that locally resembles Euclidean space but can have a more complex global structure. We start with curves and surfaces. Imagine a curve, a one-dimensional path, gently meandering through space. Differential geometry allows us to study these curves using concepts like curvature and torsion, providing a deeper insight into their shape and behavior. As we move to two dimensions, surfaces become our playground. Differential geometric tools like the Gaussian curvature describe how these surfaces bend and twist. Remarkably, this curvature helps distinguish a flat plane from a spherical surface or a hyperbolic pseudoplane. But differential geometry is not confined to 2 or 3 dimensions. It extends to higher dimensions, enabling the study of intricate structures like 4-dimensional hypersurfaces and beyond. These abstract realms find applications in fields as diverse as general relativity and string theory. Indeed, this branch of mathematics plays a pivotal role in Einstein's theory of general relativity, where the fabric of space-time is treated as a 4-dimensional manifold with curvature determined by mass and energy. Beyond physics, differential geometry also informs biology, where it's applied to the twists and turns of DNA and computer graphics, shaping the animations we enjoy today. Understanding differential geometry opens the door to a greater comprehension of the universe and the profound mathematical principles that govern it. Whether it's the curved space of general relativity or the optimized shapes in computer modeling, this subject continues to inspire and innovate. Thank you for joining us. Like and subscribe for more videos like this.